Any questions over anything at all? Well, it's been a while since we chatted about things. Things going all right? Okay. Fair enough. I assume more people will be joining us here as we get started. We'll get started since it's 9:31 according to the computer. So, all right. So, pardon me. So, obviously, the last class period we put our programs together to get the modified Newton's method to work with approximating different things, the first derivative, the second derivative, and all that good stuff. But before that, I guess it was 2 weeks ago now, we started talking about cubic splines, right? So through all of that, just to remind ourselves what we mean by cubic spline, and then recall what the solutions had to look like. We'll do that first, and then we'll go through, we'll solve one by hand, see what the algorithm is by hand, how we're solving it, and then see if we can get it into Excel and get it into R and let the computer do the work for us. So that's the plan for today. All right, so remember that the idea behind a cubic spline is that if you've got a bunch of points, I'm just going to draw a small little picture. It doesn't really matter. When we have a bunch of points that we're trying to interpolate, and remember again, interpolate means that we want to have a function that goes all the way through all of the points. It may not be feasible. Now, it is feasible, but it may not be practical. It may not be useful to send a single polynomial through all those points. We've got 6 points here for this one, so I'd have a 5th degree polynomial that would have to go through it. We're going to have one single polynomial go through all of them. Of course, the higher the number of points you have, the higher the degree goes. The higher the number of points you have, the higher the degree goes. And we've seen from other examples that it could be that you've got a nicely behaved function, but the polynomial trying to go through the points gets wildly varying, especially towards the end. We saw that with the 1 over 1 plus x squared function, right? We've seen that if you use equally spaced points and try to do more and more points, all it does is make the polynomial get worse and worse on the ends, right? So we've seen that before. So the idea behind using splines is rather than using a single function to go through all of the points, we use a certain type of function and go between points and then making sure that we have some things satisfied. So the first thing we talked about, and this is even before we did cubic splines, we talked about the linear splines and basically said, play connect the dots, right? So a linear spline would literally just be a piecewise linear function, making sure that we go through the 2 points at each point. The problem with this, of course, is what? What's going on? What do you see at especially the interior points that you don't necessarily like? You will see those corners, right? So we said linear splines, they work. As a matter of fact, that's how Excel graphs things, right? If you've ever done a line chart in Excel, that's how Excel does it, isn't it? It doesn't do anything that's bent. It just puts a bunch of sticks together. Although if you get, the small enough sticks, you can make it look curved. All right, so the next thing we did after that was rather than using sticks, we used pieces of parabolas, right? So when we did the parabolas, we wanted to make sure things were smooth. So not only did we make sure that we came to the same point, but we also said that we wanted to make sure derivatives matched, right? Now I'm going to make this look ugly at this point, right? But even to get this derivative to match, now I'm going to have to go up and come back down again, right? The way I have it drawn. So on the quadratic splines, we made sure that at each of these points, we made sure the function values agreed, and we made sure that the derivatives agreed. So it looked nice and smooth. But at those points, we might get an abrupt change in curvature, right? Notice that the way I have this particular one drawn, this one is curved down, this one is curved up, and for quadratic functions, the curvature doesn't change. The second derivative of a quadratic function is a constant, right? So we have if we look at just the second derivatives here, you'd have a discontinuity, right? Went from an abrupt change from concave down to concave up. So that was when we got to cubic splines and made sure that we not only were we making sure that the function values agreed and the slopes agreed, we made sure that the second derivatives also agreed, right? So if you've got a list of points, pardon me. So if you say you've got an x naught, y naught, and x1, y1, and so on down the line, and xn, yn, then we had the conditions to make sure that if you use S to denote the different cubics, your ith one at the right endpoint, has to equal the next one at the left endpoint, right? That says that the endpoints have to match, right? So when if I'm looking at making sure the right, so if we think about the interval going from x sub I to x sub I plus 1, I make sure that my right value coming out of the cubic polynomial going from x sub I to x sub I plus 1 matches that left-hand endpoint. And then we did the same thing for the first derivatives and the second derivatives. So those are the defining characteristics that we made to make sure that we had those conditions that were met. Now, we also went through some explanation that if you're doing cubic functions, if I've got n plus 1 points written down, right? And I think when we did this, I started at 1 rather than 0. It doesn't really matter. Notice I've got n plus 1 points. I've got n cubic functions that we would need to find. Each of them would have 4 coefficients you have to find, right? Because you got to find a constant term, an x term, an x squared term, and an x cubed term, right? So I've actually got 4 n coefficients that we have to find. But if we write our functions in a nice way, we can find the constants easily, right? We did those shifting pieces, right? So we could just use the y naught, the y1 up to the y sub n minus 1 as your constants. Not too much difficulty, right? Okay. So really we have 3 n coefficients that we need to find. And it turns out that if you go through all of your work, you're missing 2 of the equations, right? So we had to make some assumptions about what happens at the endpoints mainly to make sure that we could get all of the equations that we wanted. The example that we did, the process that we went through 2 weeks ago now was what we refer to as a natural cubic spline, saying that the curvature at the endpoints was 0, right? Okay. So the idea here is to be able to go through and figure out what the coefficients are for each of those things. And we worked through that last time. If we've got, I think we actually started with x1, y1 and went up to x sub n, y sub n. Remember when we did all of those, we had those delta values that we computed and then everything in terms of that. So let's see if we can remind that with a specific example. So let's say I give you a set of points here. Let's say that I have my x's and my y's. Let's say my x's are -1, 1, 4, 9, and 13. And let's say my y's are -2, -4, 5, 15, and 31. Bless you. All right. Pardon me. So we've got these 5 points that we want to interpolate with a cubic spline, which means we actually have 1, 2, 3, 4 cubics to find. Right? They got a cubic from the first point to the second, 1 from the second to the third, third to the fourth, fourth to the fifth. So we've got 4 cubic splines that we need to find, or excuse me, cubic functions that we need to find. to make our cubic spline. So as part of that, remember we had to calculate those deltas, the difference between your x coordinates and the difference between your y coordinates, right? So I'll write it this way. So your your delta 1 here, again, your little deltas are your difference between consecutive x values. Your capital deltas are your difference between consecutive y values. So your delta 1 would be 2. Delta 2 would be 3. Delta 3 would be 5. And delta 4 would be 4. All right. And then for your capital deltas, pardon me. For your capital deltas is the difference between the y coordinates. We would get what here? Negative 4 minus a minus 2 is negative 2. 5 minus a minus 4 is 9. 15 minus 5 is 10. 31 minus 15 is 16. Assuming I did my subtractions again. The difference between your x values. So your 2 is the 1 minus a minus 1. The 3 is the 4 minus 1. All right, so then so again, the idea behind this is that we know what the constants are going to be. Your constant for your first cubic is going to be negative 2, and you're going to use powers of x plus 1 for your other powers, right? You're not going to do powers of x, we'll do powers of x plus 1. So you'll need to calculate your coefficient on the x plus 1 term, the x plus 1 squared term, the x plus 1 cubed term. And then do the same thing for the next one. Your constant will be a negative 4, but then we've got powers of x minus 1. The next constant will be a 5, and you'll do powers of x minus 4. The next one will be a 15, and you'll do powers of x minus 9. Right? So the way we did this was we figured out what the coefficients on the linear piece and the coefficients on the cubic piece were in terms of the coefficients in the quadratic piece, right? So again, if you think about your cubic function being, say, a sub I plus b sub I times x minus x sub I, c sub I times x minus x sub I squared, and d sub I times x minus x sub I cubed. This is what I mean by powers of x minus whatever, right? Then it's easy to see what your constants have to be, because if I plug in the x sub I better get the y sub I associated with it, because the other terms cancel out, right? I know it's been 2 weeks, but we did all this stuff before, right? Get all these coefficients, or all these equations. All right, so we did all of this work. We found out that once we have the C's, we can figure out the B's and the D's from the C's, right? Your D's were difference between consecutive C's divided by 3 times the deltas. And your B's were a little bit more complicated. It was ratio of your deltas minus the little delta I over 3 times 2 times C sub I plus C sub I plus 1. We did all of that work before, right? Hello. All right. So notice that again, we know what the A's are because the A's are just these, right? So for your first cubic, your A1 will be negative 2. Your X1 is negative 1. So you would have a negative 2 plus whatever this is times x plus 1, whatever this is times x plus 1 squared, whatever this one is times x plus 1 cubed, right? And then do the same thing for the next ones. So the A's aren't hard to calculate. We can figure out the B's and the D's once we have the C's. So everything's going to be boiled down to trying to figure out what the C's are, right? All right. So for your natural cubic splines, this was going to help us start these things. And then we'll talk about other cubic splines later. For your natural cubic spline, that says that, pardon me, your curvature, oops, and I'm going to start counting at 1, even though I wrote my initial points with zeros. Your initial curvature at the initial left endpoint is 0, and your curvature at the right endpoint is also 0. So the way I know I changed up my numbering a little bit because the way I developed it in class 2 weeks ago is different than the way they developed it in your textbook, because I just thought it was a little bit easier to see what was going on. But the idea here is that the curvature at the leftmost point is 0, and the curvature at the rightmost point is 0. That's what we mean by a natural cubic spline. There are other splines that we'll talk about. Splines are used in practice, by the way. Font generation, for example, uses splines. So all your different types of fonts that you do splines, but they're variants on cubic splines. If you do anything with what are referred to as vector drawing programs, a lot of times those use splines as well to draw them, where you can connect the dots and then change the curvatures and get everything matched up. All right, anyway, so this is what we mean by a natural cubic spline. So what this forces is, of course, that your very, very first C value is going to be a 0. Right? If you're going to make the curvature be 0 at the left endpoint, remember your curvature is given to you by the second derivative. I should say concavity, I shouldn't say curvature. Curvature is a slightly different word. You've had Calc 3, you know that curvature is not only bend, not only does it take bend into account, but it's how quickly it bends, right? You do bending divided by arc length. Look at me like I'm nuts. Some of you've been in Calc 3. I know you've been in Calc 3. You do how much it bends, and then you divide by how long it took to bend. Right? It's a derivative. It's for vector valued functions, the derivative of the unit tangent vector over with respect to the arc length. That's just a measure of how quickly it bends, right? Your unit length of some sort. Anyway, the second derivative tells you something about how the function bends. That's the idea. We're saying that there is no bend, there is no curvature, there is no concavity at the left endpoint and the right endpoint. So that forces that first C value to be 0. Okay, cool. All right, so then using this information, we were able to come up with a system of equations to solve. We know that the first one has to be 0. We also make a dummy one at the end, making a last one equal to 0. And we get a system of equations to solve that looks like the following. So, pardon me. My first coefficient on my C will be a 1. All the rest of them will be zeros. I'm writing it as a matrix equation, so I'll remind. And then I'll fill in this in a second. So the first equation that we solve talks about that first curvature being 0. So that's why we have a 1 here and then a bunch of zeros. Remember when you multiply matrices, you take rows and match them with columns, right? So when I take row 1 times column 1 here, I'm just talking about C1. We know that first curvature is 0, so I get a 0 here. To help us solve these things, notice that, for example, let me go back up here. Notice in your B sub I and your D sub I, they're in terms of the next C, right? So to calculate the very, very last B and the very last D that we need an extra C on the end. So there's a dummy C on the end, if you will. Again, since we're doing the clamp spline, I'm assuming this very, very last one here will also be 0. Not clamped, sorry, natural spline. There is a notion of clamp spline. We'll talk about that on Thursday. So again, these are just, again, re-emphasizing that the curvature at the ends has to be 0, right? All right, so then for the other coefficients, remember we had those patterns with the deltas that we came up with. In the very first row, we get a delta 1 here. We get a 2 delta 1 plus 2 delta 2 here, a delta 2 here, and then zeros the rest of the way across. And then we shift over and down, right? We get what's referred to as that tri-diagonal system. Remember, for your matrices, for square matrices in particular, your main diagonal is the one that runs from upper left to lower right. So we get that main diagonal is going to have numbers on it, and then we'll have numbers running down the diagonal line right directly above the main diagonal and right directly below the main diagonal. So that's what we call a tri-diagonal system. Our goal today is to come up with an algorithmic method for solving this type of system so that we can put it in Excel and put it in R or any other programming language you'd like. Okay, so that's our goal for today. That's why we're going to go through it by hand with a specific example and then try to see if we can get it coded up. Okay. All right, so we're going to move this diagonally down and to the right, and our subscripts are going to go up by 1 each time. Right? So the next row will look like a 0, a delta 2, a 2 delta 2 plus delta 3, a delta 3, and then zeros the rest of the way across. The next one will be 0, 0, delta 3, 2 delta 3 plus 2 delta, whoops, I forgot my 2 on that one, sorry. 2 delta 4. There'd be a delta 4 in this column that I didn't put in there. 0, right? Continue down. I'm going to write in the last row here. We'd have zeros here until the very, very end. Your last one's going to be a delta n minus 2. A 2 delta n minus 2 plus 2 delta, oops, I didn't leave myself enough room. A 2 delta n minus 2 plus a 2 delta n minus 1, and a delta n minus 1 here on the end. All right, so that's a lot of numbers that we have in here. Let's see if we can set up exactly what we, and I gotta still fill in the right-hand side. I'll do that in a second, okay? But let's see if we can get our matrix set up for the points that we had. Okay, so I'm gonna scroll up, and I'll scroll, well, I don't need to scroll very far. Let's see if I can get rid of this. Here are my deltas, right here. Okay, let me grab that and see if I can grab this and copy it down here. Ooh, hey, that was fun. I'm gonna try to let's copy and where's my paste button? Do this way, paste. There we go. Cool. All right, here are my points. Right, my points and my deltas. I lost my capital here on my whoops. Lots of whoops today. Lost my drawing there. There's my capital delta, right? All we need to fill out our matrix is our little deltas. Okay. Again, we have 4 cubic splines that we're going to find, that we need to find. But remember that last C that we have is a dummy one to help us calculate the B's and the D's for those, right? So we're going to have 5 C's to find, so we'll have a 5 by 5 matrix to start with, right? So your first row would just be 1, 0, 0, 0, 0, and your last row will be 0, 0, 0, 0, 1. Right? Now let's go across and fill out our other rows. So, pardon me. Notice that we only have 3 other rows to fill in, so it'll basically be these 3 rows. Notice that n is your total number of points. Your last delta that you put in is delta sub n minus 1, so that's delta 4, which is actually in this third row, right? So we only have 3 rows to do here. So your delta 1 is 2. Your 2 times delta 1 plus 2 delta 2 is 4 plus 3. We get 10 here, right? Yeah. And then 3 here. Shift over. That one's going to be a 3. 2 times 3 is 6. 2 times 5 is 10. 6 and 10 is 16. Right? Oh, yeah, and the rest of these are zeros. And then we had a 5. And then finally, our last one we have to put in here is 0, 0, 5. 10 plus 8 is 18, and 4 here. Everybody see how we filled out the matrix? Yeah. Okay, so where did this 2 come from right here? What's this 3? Okay, and this 5 is delta 3, right? It's just delta 1, delta 2, delta 3. And then these are just the next one. This is delta 2, delta 3, delta 4, right? And then this number in the middle is 2 times that one plus 2 times that one. So 2 times 2 is 4, 2 times 3 is 6. Added together, you get 10. 2 times 3 is 6, 2 times 5 is 10, 6 and 10 is 16. That's where those come from. So again, down this diagonal, your deltas, down this diagonal, just your next deltas in the sequence. 1, 2, 3, 3, 2, 2, 3, 4, and then you're done. All right.
So why does it go 2, 3, 5, 0, not 2, 3, 5?
Well, remember the very last one is n minus 2 and n minus 1, right? So the last row is always going to be zeros up until a 1. We stop at the n minus 1 delta because there's not a delta sub n. If you've got n points, there's only n minus 1 differences you can calculate. So there wouldn't be anything to put on that last one.
Okay.
All right. So far, so good? All right. So now going back, we'll fill out the rest of this equation here in a second. Remember on the right-hand side over here, we also had some equations to do, right? So these were 3 times delta I plus 1. Well, I guess it's not I plus 1. This will be delta 2, because that is the next. That is I plus 1 over little delta 2 minus capital delta 1 over little delta 1. So the next one would be delta 3 over little delta 3, capital delta 2 over little delta 2, and so on down the line. The very last one will be capital delta n minus 1 over little delta n minus 1, and then the n minus 2's here. It's 3 times the difference of consecutive ratios of deltas, right? The first one we're doing 1 and 2. The next one we'll do 2 and 3. The next one we'll do 3 and 4 until we get to n minus 2, n minus 1. We have to stop at n minus 1. That's all the differences we have, right? So we have to stop. Okay. All right. So in this problem, I write this as a matrix equation. Oops. Again, first one is going to be 0. Last one's also going to be 0, right? All right, so the way we have this one is capital delta 2 over little delta 2. 9 divided by 3 is 3. Minus capital delta 1 over little delta 1. That's negative 1. So it's 3 minus a minus 1. So we get 4 times 3. So we get 12 for that one. I made up this problem ahead of time. That's why the numbers are coming out a little bit nicer. Okay. All right. So the next one we would do, so for the first one, we looked at these two, right? For the next one, we go to the next ones in the sequence. 10 over 5 is 2. 9 over 3 is 3. 2 minus 3, negative 1 times 3 gives me negative 3. Last one. So 4 minus 2 is 2 times 3 gives me 6. I heard you say 6, so I knew I was right when I got to the end. 16 divided by 4 is 4. 10 over 5 is 2. 4 minus 2 is 2. All right, cool. So far, so good. Yes? No? All right. So now we need to solve this thing. This is why we want the computer to do this eventually, because this is not fun to all necessarily do by hand. But I want to go through it by hand so we can generate what the algorithm has to be. Okay? That's the whole idea of why we're doing this. That and I'm mean. All right. So now, if you remember doing elimination ideas, I already know what the C1 has to be. The C1 has to be 0. I don't need to worry about that one anymore. But also remember, if you're doing row reduction type of ideas, I can make this a 0 here by doing negative 2 times that and adding down, right? Elimination. If I do negative 2 times that, I get a 0. Added to that just gives me the same value, doesn't it? So I can get rid of this. These don't change because I've got zeros right above them. And I eliminate that entire column. So I don't really even need to pay attention to that column at all, or this row, because I can eliminate this 2 off of there immediately, right? And it doesn't change anything else. All the other numbers stay exactly the same. I can eliminate the 2, and it doesn't change squat about the rest of the matrix equation. Likewise, I can do the exact same thing here. I can get rid of this 4, right? By taking negative 4 times that and add it to that, right? Notice everything else in that row is a 0, so it doesn't change anything else. So I can eliminate that entire row and that entire column. So we can really reduce this down to 10, 3, 0, 3, 16, 5, 0, 5, 18 times C2, C3, C4 equals 12, negative 3, 6. I know C1 is 0. I know C5 is 0. And if you don't like the elimination idea, think about doing substitution. If you don't like elimination, think about substitution. If I take C1 equal to 0 and plug it in here, I get a 0. Right? So it makes that go away. And it didn't change any of these things. Likewise here, if I make C5 equal to 0 and plug it in here, it makes this go away. It didn't change anything else. Right? So the idea here in this, and now again, we're generating a method to solve this specific type of system, right? That's our whole goal here. If we change the type of system, we may have to change the method. Okay? But for this type of system, I can throw out the first row, throw out the second row, throw out the first row, throw out the last row, throw out the first column, throw out the last column, and keep all the numbers the same. So far, so good? Okay. Now we can do elimination. And I think it's a little bit easier here to do a forward elimination and then a back substitution idea. Okay? The first thing you would need to do, or we would want to do, is I would use this value here to make that a 0, right? That would be step number 1, right? You can change it into a 1 to start with, but let's try to simplify the number of steps that we have to actually do, okay? Okay. So to make this a 0, I would need to take this row, I would need to multiply it by -3/10, right? We agree with that? Okay. Take -3/10 times that row and add it to the second row. Right? Agreed? Okay. This -3/10 will get multiplied by absolutely everything across, won't it? Okay. So we won't change the first row at all. Oh, I'm not going to worry about writing it. I'm going to do this as an augmented matrix. I'm not worried about my C's all the time. Okay. So it doesn't change the first row at all, but we get a 0 here, right? I would have whatever this is going to be, -9/10 and then 160/10. So I'd have 151/10, right? This is still a 5. What do we have here? I've got -36/10 minus 30/10. So that's -66/10 or -33/5. Yeah. Okay. And then that did not change the last row either. All right, so that was one step. But let's think about how that step worked. Okay. We looked at the ratio of these two terms, right, to make this a 0, right? We agree with that? So we did negative of this one divided by that one, right? And then we used the same coefficient all the way across. So I'm trying to think about how we would do this in Excel, right? I want these to be something that was a relative cell references because I want to be able to shift this down, right? But as we go across, I don't want to change the ratio, right? So I would want to keep the column the same, but not the row, so that we can copy down, right? Okay. Once I've got this number changed, then I need to do this one, right? And I would do the exact same process. The problem is that it's been shifted over a column, right? It'd been nicer if I want to just do copy and paste down in Excel, it'd be a lot more convenient if I have it all in the same column, right? You agree with that? Be a lot more convenient, okay? So if we think about this in Excel, it'd be a lot nicer. So remember again, our tri-diagonal system, pardon me, started out with delta 1, 2, delta 1 plus delta 2, and then delta 2. And then we shifted over, right? It was delta 2, 2 delta, oops, I keep forgetting that 2 on there. It's shifted over that way, right? But in Excel, wouldn't it be a lot easier if I deal with this and shift it over one, right? Okay, so let's think about how, remember I did, oops, I need to scroll this down so you can actually see what I'm going to point to. Okay. Remember here, we're going to get rid of this. This column's going to go away to start with, right? But I probably don't want this one necessarily to be gone when I shift this over, because then this is going to end up here. Or if you'd rather, think about that going that way. It doesn't matter which way. Right? I want to think about them being stacked, correct? Okay. But this 10 came from that value, didn't it? Right? And then we try to get rid of this one. So if we think about stacking them in Excel, if I've got my delta 2 here, and then my 2 delta 1 plus 2 delta 2 here, 2 delta 2 plus 2 delta 3 here, delta 2, delta 3 here, then I would need to do negative of this over this, wouldn't I? So I would have those columns off by 1 when we're typing it in. We agree? Okay. So let's see if we can type this into Excel real quick and put these things together. And then see if we match with that first row. And then see if we can just copy down and use Excel that way. Okay. All right. So let me switch over. Let me retype my X's and my Y's here. The X's were negative 1, 1, 4, 9, 13. And the Y's were negative 2, negative 4, 5, 15, 31. Oh, I probably need to zoom in so you can actually see what I'm doing. Sorry about that. Like I said, lots of oops today. So all I did there was just type in the points that we started with. The X is negative 1, 1, 4, 9, and 13. The Y is negative 2, negative 4, 5, 15, 31. How can we compute each of the deltas, what we want to do? How would you calculate the first delta here? So I would do, which ones? I think A3 and A2, right? Yeah. Okay. A3 minus A2, we'll do that one, right? Now notice if I copy that over one spot, that will do B3 minus B2, right? That gets the Y deltas. Yeah. So all I did was type it in the one spot, copied it over here. Now I can just highlight and copy down and get the other ones that I wanted. So far, so good? We did all that by hand, but now we've got Excel doing that. And notice, if you put more points here, you can just copy and paste that down. It'll do all those still for you. So once you have this set up the first time, you should be able to do bigger problems. You not have to change much except for copy down. It's one of the nice things about it. Is that your back?
That was my shoulder.
Oh, it was your shoulder. It's like I heard that pop from over here.
The lasting effects of swimming.
I was going to say, is that a swimming thing? Anyway. All right. So remember then when we set up our system, let me go back over to what the system looks like. Our system's going to have I don't need to worry about the first row at all, right? Because we know what that is, correct? Okay. Our second row has delta 1, 2 delta 1 plus 2 delta 2, delta 2. The next one has delta 2, 2 delta 2 plus delta 3, and delta 3, and so on down the line, right? Okay. But again, we want to stack these so that we can copy and paste easily. So this one, again, is going to be your delta 1 here, right? The next one over is 2 times delta 1 plus 2 times delta 2. And this one's going to be 2 times delta 2. Or not 2 times delta 2, just delta 2. Sorry. And again, this should look like, if I go back over to here, 2, 10, 3. That was what we had, right? right? Okay. If I go back over here now and just take this and pull, I get the other ones that we had, right? They're stacked now. They're not shifted over as a tridiagonal system. They're just stacked. But those are the values that we had for the rows that we're interested in. Remember, first row don't care because it's 1 and a bunch of zeros, and the constant or the coefficient is equal to 0. Last row don't care. It's a zeros and a bunch of zeros and a 1, with the last constant equal to 0. So that coefficient is 0. So I don't need to worry about the first and last rows. I just need the middle 3. But again, if you've got a bigger system, I can just copy and paste down. Yeah? Okay. Finally here, I'm going to put my constants in. My constants were 3 times ratio, right? Capital delta 2 divided by little delta 2 minus capital delta 1 divided by little delta 1. That was how we got our first coefficient, our first constant, I mean. Delta 2, capital Y delta 2 over X delta 2 minus Y delta 1 over X delta 1. Yeah. That should give us 12. And then the other 2 should pop out as I copy this down now. If I can grab it. There we go. Those should be the values that we have, right? Yes. Go back to the 10. What do you have?
I was wanting to see G2.
The G2 is just equal to D2. All right. Now again, remember, this one here doesn't matter. Remember, that was the one we were able to cancel off from the row above, right? So I'm not going to use that one at all. Also, this one doesn't matter. Because that one would be, again, canceled off, right? Okay. So right below this, I want to try to generate exactly what we had here. Okay? And in particular, we should have zeros in front of it, but that's okay. So what do we want here? Well, remember that the first row doesn't change, right? When we do this, when we start, the first row doesn't change at all, correct? Okay. So this, I'm just going to write this as, whoops, not all the way across. I'm just going to copy it back down again. So I was just going to say equals G2 right here and copy it across. I'm just trying to keep it looking like what we have, and I'm going to delete that out of there. Now, how did we get this one? When we're done, this should be a 0, right? I need to get rid of this 3, correct? I need to get rid of this 3, working off which value? The 10, right? I gotta get rid of this 3, working off the 10. Once we do that, this value right here is going to change to something, and that's what we're going to have to use to kill off the 5, right? Okay. So this value here should be negative of what? What coefficient did we use? The negative of what? 3 over 10, right? So it'll be the negative of G3 divided by what? H2, right? Now remember, this ratio, I need to multiply it by everything in the row, correct? So I don't want it to change as I copy across. I do want it to change as I copy down. So we use that absolute cell reference on the column letter. So if I go back over here, I'm going to put a dollar sign in front of my G and a dollar sign in front of my H. I don't want that to change, right? Right? I'm going to use the same ratio all the way across. If I copy across, it'll change the column unless I tell it absolutely to stay in that column. That's what the dollar sign does. All right, I'm going to multiply this now by what? Yeah, the H3, right? The 10, right? And then add it to what? The G3, right? I need to add it down, right? Okay. Now, we'll have to fix this for this one, right? Because everything's in the same column here versus going across columns. But this should work for this one and this one, right? So if I hit enter, what number should I get out of this? It should get a 0, right? Yay, cool. If I copy this across, I get 15.1, which I believe is what we got. Wasn't it 151 tenths? Yep. And then the 5 stayed the same, which it should. Right? That shouldn't have changed. Now if I copy this down one row, I should get the other one as well, which we didn't do. Right? But notice again, we're getting zeros when we're supposed to. Right? These should be zeros when we're done. Again, if you've got more points, you can copy this down. You'll have to insert some rows. I probably should have gone off to the right, but I've zoomed in, right? If I would have gone off to the right, you could have just copied down. So if you're setting this up for yourself, you might want to move your stuff over to the right rather than right below it. But I want to make sure everything was on the screen for you so you can see it. Is this okay? Now again, this last one here, I've got to keep everything in the same column, right? So if I go back up here and just grab the text, oops. I still want the G3 over the H2, right? But I want to multiply this by what? Not H2, but what do I want to do? I'm doing -3. I want to get rid of this. I want to work off of this 12 and work down to the -3. Right? I'm trying to work in this constant column. This is the ratio I want, but what do I need to multiply this by now? K2, right? That's that top constant. I need to change this H2 to a K2. And then what does this get changed to? K3, right? I need to add straight down, right? Not curved. This curved. Change the H. So that used to be H2 next to the multiplication sign. So I changed it to a K because I'm working off the constants now. Again, when we're working in the other,
I just didn't see how we got the K values up there, the 12, -3, 6.
those are the ratios of your deltas.
Okay.
That is subtract those 3 times. The first one is 3 times capital delta 2 over little delta 2 minus capital delta 1 over little delta 1, and then just copied it down. Yeah,
I'm sorry, how did you get the I column 3, 5, and 4?
So this one was equal. So remember, this is your first delta, so that was equal to D2.
Yeah.
Right? This is your second delta, so this is just D3.
Okay.
And then just copied it down. Again, I had to change this one slightly because remember, when we're working over here, we were diagonaling down a column, right? On this one, I have to work straight down. That's why I had to edit it, right? I couldn't just copy it across. I could have copied it across and then edited it, but because that was easier just to do it this way. I may have been wrong with that, but anyway. And I believe we did get negative 33/5 there, right? That's 66 over 10. Okay. Copy down, get the last one. Yay. Okay, cool. So far, so good? Yeah.
Can you go back to case 7 one more time?
Sure.
Thank you.
Mm-hmm. All right. Is that 4 in the lower right column or lower right corner really a 4? No, it's not. It's a 0, right? Remember that was the one we eliminated? You're going to have extra pieces in here because of the way we stacked things, right? But remember, the reason why I have this in here right now is so that we can just copy and paste down so that we can see those pieces automatically filled, right? But remember, this 2, not really here. This 4, not really here. Those are zeros, right? We agree? Okay. So think about what the equations we have to solve here. Again, if I draw on here, this is not here. This is, whoa, that was weird. This is not here, right? Agreed? Okay. So notice here, I've got this value right now. I can solve for C, can't I? C4, can't I? I just need to take what to solve for C4? What needs to be divided? You can just tell me the numbers. What needs to be divided to figure out what C4 is? Yeah, the 6.9 needs to be divided by the 16.4, right? This last row right here says that 16.4375 C4 equals 6.9375. Right? That's what that says. Okay. So I just need to divide to get that one, right? What does the second row say? Okay, I guess I won't get rid of that. What does the second row say? This one, what was this row say? Yeah, good. It says 15.1 C3 plus 5 C4 equals negative 6.6, right? Once we have this one, we can substitute it back up here and get this one, can't we? And then it's the same process. Once we get this one, I can substitute it here and get that one, right? Oops. That didn't do what I wanted it to do. All right. I guess I'm going to leave the writing on there because it's not letting me get rid of the writing. All right. Oh, or I could do that. Great. I'll just move it over. Great. Fantastic. It's out of my way now. All right. So, can I get rid of it now? Can I select it and get rid of it? No. That was weird. Anyway, doesn't matter. It can stay there. All right. Anyway, what do we want to do now? I said we want to do this divided by this first, right? Let me scroll up a little bit. There we go. All right. So to get this one, I want to do this divided by, do the K8 divided by the H8, what we have. Right? Yeah. Okay. And now we'll work up. How do we get the next one? What do we do? Yep. Okay, so we'll need to do the negative 6.6, and I'm going to have to divide by the 15.1, but I got to do something else in the middle. Yeah, I got to do 5 times what? Times this thing we just found, right? I got to take this value that we found for C4, which is weird because that's not the number it should be. That's okay. We'll figure it out. Take this times the C4, right? So that's going to go in here. I got to multiply by the 5, subtract it over, and then divide, right? So let's put some parentheses around this. I need the negative 6.6. That's what's in K7. I've got to subtract 5, right, times the value we just found, right? So again, the idea here is I found out what C4 is. I'm plugging it into the equation. Remember, this equation is 15. For heaven's sake. Oh, it's because I'm in a. I'll do that here in just a sec. Okay. All right. That's okay. So remember, the second one is 15.1 C3 plus 5 C4 equals negative 6.6, right? Right? So we're taking this, moving it to the other side, and then we're going to divide, right? So we have C3 equals negative 6.6 minus 5 times C4, all divided by the 15.1, correct? So all I need to do is, that's where the negative 6.6 is, that's what's in K7. The I7 is the 5, the C4 is the M8. I still need to divide this by what? The 15.1, which is H7. Right? Here's what your, that's what the other one looks like, Matt. Yep. And now you do the exact same thing for the next equation, right? I need to plug in this value times the 3, subtract it over and divide. It's the exact same formula, so all I need to do is just drag this up. These numbers should have come out to be nicer, so I must have made it to error somewhere when I was playing with the numbers earlier. But that's okay. I mean, we got the numbers what they are. Is this okay? These are your C coefficients. There's just one of them that you need is missing. This is C2, C3, C4. What's the C1 again? 0, right? So the top one's missing. The C5 is also 0, but remember the C5 is a dummy one. We don't actually ever use it. We're just using it to solve the system. So far, so good? Okay. All right, now we can find the other one. Now when we're done with this, we can figure out the other ones. So these are your C's. These are your C's with a 0 in there. Oh. Apparently I shouldn't have scrolled. All right. Okay, so now to find your, let's do the B's and the D's. So we have those equations for the B and the D. So remember your B was the ratio of your deltas minus your delta I over 3 times 2CI plus 1 plus CI. Nope, other way around. CI plus CI plus 1 there. Sorry. Okay. Those are your B's. Again, this is why it's probably easier to go across on your screen rather than having piecemeal together. I'm just trying to keep everything on the screen for you so you can see what's going on. Okay. If you change this up, you probably have to change up your values. Bless you. All right. So your ratio of your deltas, whoops, I need to put this up here. Remember that this one's going to, I'm going to type it in here just so that it reminds us. Remember the first C value is a 0, all right? Ratio of your delta. So going back over to where the deltas are. ratio of your deltas. So it'll be this E2 divided by D2. And then minus your D2 times 2 times the C plus the next C, right? Right? So 2 times this C plus that C. What's that? Did I forget to divide by 3? Oh, thank you. There we go. That better? All right. And then we should be able to just copy this down and get those values. Again, like I said, this is probably helpful if you do it all the way across so you can see it all on the same line. I only shifted down so we can try to get everything on the screen at the same time so they can actually see it. Okay,
Where did the 0 come from again?
remember, the first C is 0.
Oh,
Yeah. So I just typed in a 0. I actually didn't have to type in anything. It'll treat it as 0 if I would have left it blank. I was just trying to show you what it looked like. It's okay? Finally, the last one, remember your D's are difference of consecutive C's divided by 3 times the little deltas, right? So let me just zoom slightly so that we can get this on the, oops, where'd my D values go? I typed that in there earlier. Oh, whatever, I'll type it back in. All right, so what should go in here for the D's? So what's one to C2? The M6 here, right? Minus M5 and then divided by 3 times D2. Yeah, this one up here. Right? So difference of consecutive C's. So your consecutive C's are, the first 2 consecutive C's are M6 and M5, right? Okay. And then again, once we hit enter, we should just be able to copy these down and get those. So when I was playing with this earlier, I must have messed up something. Okay. Yeah?
Can you go back to the game value?
The first one?
Yeah.
Yep. Okay. All right. So let's see what this actually ends up looking like. Okay. Now, Excel doesn't graph things nicely. It'll take points and connect dots, but as far as actually graphing functions, it won't do it nicely, right? This is why we're going to convert this over to R next time. All right. But I wanted to go through the Excel idea so that we can actually get these values out and mainly practice with Excel too. All right. Anyway, remember that these are the coefficients for your different functions, right? But we got those shifted ideas. So again, your first one's going to be powers of x plus 1. Your second one will be powers of x minus 1, powers of x minus 4, powers of x minus 9, right? So your first function, I'm going to need my y values. I got my y values in my paper. So your first one, oh my heavens, I wish I wouldn't wrote on there now. I can't get rid of it. I mean, there's probably a way to get rid of it, but I'm not finding it. All right, so your first one, your first y value is -2, right? Your first b value is, nope, won't let me do it. This is a minus. 1.91537 times x plus 1, because your first x value was -1. Your next one, your C is 0, so there isn't an x by a plus 1 squared term, and then a plus. That was fun. A plus 0.228842 times x plus 1 cubed. Right? The next one, your first y value was -4, and you have powers of x minus 1. So your next one is 0.830736 times x minus 1. Your C value is 1.37052. Oops, 373,052 x minus 1 squared. And then I lost my D. Hello? What are you doing? Good grief. Apparently you should not write on Excel. Like I just said, apparently you shouldn't write on Excel. Minus 0.21665 x minus 1 cubed. Right? The different coefficients there. Yes, Abby.
Did the minus 1.9 have a square with it for the x plus 1?
This one? No, remember the B values are the linear terms. These are your coefficients on the linear terms. These are the coefficients on your quadratic terms. Yeah, lady.
Where are we getting the like the -1 for the x plus 1? Or the 1 for x minus 1? Like where is that?
Here?
Yeah.
So remember, this is your first x value was a -1, and we're doing it as powers of x minus the
it's
x
just the
value.
x values.
Yeah, it's just the x value. It's x minus the x values. Yeah. Yep. So the other the other two, then you would have, I can't remember what the next y value was, 5? 4. So you'd have a 4 and then a plus 3.219 times x minus 4.
Yeah, you're right. It was 5.
Yeah.
Yeah, sorry.
I thought it was a 5. Yeah. The x was a 4, right? Yeah. So you would have S3 is 5 plus 3.21937 x minus 4 minus 0.57684 x minus 4 squared. That is really bad handwriting. And then plus 0.066593 times x minus 4 cubed. It'd be nice to graph these and actually check to make sure that these connect, right? At least I think it would be nice to do that, right? So we'll work on this next time, but let me just show you real quick. I do this in R, if I can open it up. Thought we would have moved it a little quicker today, which is why I didn't have this loaded, because I thought we were going to create our own. That's okay. Maybe. There we go. See what this looks like. Hopefully it will. Hopefully the values that we come out of this will match. So the x's were... By the way, there is a cubic spline function built into R as well in the Pragma library. But it's no fun if you can't do it yourself. Maybe you can't find the function cubic spline. I just entered it. Oh, that's right. I did have an S in there, didn't I? Thanks. I don't remember what I called my own function. There it is. Oh, these numbers should have matched, and it doesn't look like they do, so we might have some error in our Excel formula. Oh, they don't match, do they? I don't think these are the same numbers, were they? They're close. Yeah, there must be some small error in there, but you can see matching up the points now. And see why R might be a little bit preferable, because I can actually graph the thing rather than having to go through Excel. So there might be a slight error in our Excel formula somewhere along the way. It might be a rounding thing too. When I did it the other day, it came out exactly the same. So it's probably just some little tick of something that was done something not quite right. But this is the idea. So next time our goal is to see if we can get the R code done. And I know I already did it, but we'll do it together. Make sure we can understand what's going on, so that we can do one of the homework problems that I want you to do, and then you get your next major assignment done. You're not going to be tested as a test on cubic splines. It'll all be outside of class stuff. Because it's just a lot of formulas to try to memorize and type in stuff. So that doesn't seem like a good use of time. So, all right. Anyway, we'll see you on Thursday, if not before.